All right, so it's 2 days after the AP Calculus AB exam, and the questions have been released by the College Board. So I am going to put myself to this torture and try to solve as much of these as possibly can, so you know what the answers are. Let's see how well I could do this. All right. Um, right here, I have the exam put up right here on the left, and I have my work on the right. Um, for a calculator, I'm just going to use Desmos so you can see my work. All right. Question one. From 5 a.m. to 10 a.m., the rate at which vehicles arrive at a certain toll plaza is given by A of t is equal to 450 times the square root of sine of 0.62, where t is the number of hours after 5 a.m. and A of t is a measure in vehicles per hour. Traffic is flowing smoothly at 5 a.m. with no vehicles waiting in line. Okay. Write but do not evaluate an integral expression that gives the total number of vehicles that arrive at the toll plaza from 6 a.m. to 10 a.m. So I like how they give these numbers t is equal to 1 and t is equal to 5. And when I did the BC exam, I just referred to them as 1 and 5. And it's a good thing to note the AB and the BC exam, they share a bunch of the same questions. Um, but anyways, uh, if A of t, right? Nice. I lost track of my pen. Oh, there we go. A of t is a rate, right? Um, yeah, A of t is the rate. So then now, if you take a rate and you multiply it by some sort of time, you get the amount, right? So let's say you're driving at 60 miles an hour, right? And you take 2 hours to ride at 60 miles an hour. How many miles have you driven, right? You just the hours cancel each other out, right? So basically, what they're trying to do is they're trying to make you write an integral expression out of here. Oh yeah, which they say right here, what an integral expression, right? So you have this rate and you multiply it by time. So this rate is in vehicles per hour, right? So you have vehicles per hour, and then you multiply by the time. In this case, it would be dt, right? Dt is just a small amount of time, right? And then what you get is the number of vehicles. And how we determine the number of vehicles is determine the time our limits of integration, which go from 1 to 5. So that is question A right there. Just from 1 to 5, you take the rate. From 1 to 5, you take the rate, you multiply that small, infinitesimally small amount of time, and then you get this answer right over here. Let's go on to question two. Try to keep the same. I can just use my mouse and move it up and down. There we go. Question two. Find the average value of the rate in vehicles per hour at which vehicles are at the toll plaza from 6 a.m. to 10 a.m. Okay, they're trying to confuse you here. I don't know why they said average value. When you think average value, um, most people they memorize formulas, which I highly recommend not to do, but they think of this, f of x dx. And this is what they're not asking. So you could have fell for that trap very easily. But in this case, what they're trying to do is average value of the rate. So this is in rate as a whole overall, right? A of t is a rate, right? It's vehicles per hour. So vehicles per hour. Oh, oh, actually, okay, I probably messed this up on my exam. Well, uh, okay, let me show what I did and how I did it incorrectly. So here's what I did. I said a of 5 minus a of 1 over 5 minus 1. But now thinking about this, that is completely incorrect. Okay, we all make mistakes. So actually, it is this. Never mind. Um, I should have done this beforehand. It is average value, and I was just tired, I guess, on the AP exam. I don't know. But yeah, let me just rewrite that again. So it's 1 over b minus a of the integral a to b of f of x dx. All right. And here, what they're trying to do is the average value of the rate. So like what they're doing is finding this area, which is in vehicles, right? So average value essentially is you take this area under the function and you divide it over that x interval. And what that gives you is the average value if you like to draw just a rectangle. So let's say you had something like this, right? The average value would give you like some sort of line where you can draw across, and that rectangular area would be the same area as if you were to take the integral, right? So that's what the average value gives you. So I thought I was clever by taking the slope, but apparently that's not the case. Um, but anyways, if you take the integral of the rate with respect to dx, right? What is it? It would be from 1 to 5 of a of t dt. And then you would divide by that interval, which in the case is 5 by 1, 5 minus 1. And then let's put this into decimals real quickly. Decimals.com. So integral from 1 to 5. I'm just going to say a of t is equal to 450 times the square root of sine, I'm pretty sure 0.62t. There we go. This is a weird function. Okay, but yeah, this makes sense. Amplitude is 450. All right. Yeah, that's right. But anyways, I'm going to take the integral of a of t dt, and then I'm going to divide that by 5 minus 1. And in this case, it would be 375 0.54. Oh, did I say it around? Oh no, they didn't say it around. So this would give you vehicles, and then 5 to 1, that's a rate, or sorry, that's a time. So this will be vehicles per hour. And oh, we have to round to significant, not three significant digits. So 375.537 vehicles per hour. So that's that right there. Okay, let's go on to question C. C. Okay, is the rate at which the toll plaza at 6 a.m. increasing or decreasing? So they're saying is A of t, because remember A of t is the rate. Is A of t increasing or decreasing, right? Right? So how do we tell if a function is increasing or decreasing? Well, in calculus, you use the derivative, right? So if a prime of t is greater than 0, then a of t is increasing. Well, think about it, right? If the derivative is greater than 0, that means you're saying the derivative is slope, right? Then you're saying the slope is greater than 0. Well, if the slope is greater than 0, it's going to have a positive slope, and the function increases, right? And similarly, if you say a prime of t is less than 0, then a of t is decreasing. And think about it, right? A of t is the derivative. You're saying the slope is less than 0. If the slope is less than 0, then a of t is decreasing. So, what we need to do is we need to take the derivative of at t equals 1, right? So then now I want to see if I can actually just take a prime of 1. So here we get, I think I got some similar answer here. A prime of 1 is 148.947, and that's greater than 0. So therefore, the rate is increasing because a prime of t or a prime of 1 is greater than 0. And the explanations you need for calc are pretty self-explanatory, so that's not a big issue. I mean, you don't have to be super specific. You'd be like, okay, the derivative, you're saying the slope is greater than 0 there. Saying the derivative at 1 is greater than 0, so it's increasing at that function. You can't say anything more. So you could just be like that. It's increasing because a prime of 1 is greater than 0, and you would get the point. D. Okay, honestly, I'll come back to D later. I don't want to deal with D now. I have to think about it a little bit more before I move on. Anyways, let's go to question 2. See if I can. There we go. Bring this down. Let f and g be functions defined by f of x natural log x of 3 and g of x to the fourth plus 2x cubed. Oh, and by the way, this is the first time I've ever seen this problem, so that's interesting. Okay, find the area enclosed by the region f of g. Okay, so think about areas if you want to like, the integral gives you an area, right? So like if you just take the integral, like this is from a to b, right? This gives you, this is just the integral of a to b. Let's say this is like f of x. You can't read that at all. A to b of f of x dx, right? So um, here, what you do is like, okay, let's say you have this function and then now you have this function from a to b as well, right? Now you just take the top function and get that black area, and then you take this bottom function, you take that red area, right, that integral. You take those integrals, you subtract them from each other, and the remaining is this thing between the two curves, right? So then what you need to do is you need to subtract two, but then now you need to know which one is f of x and which one is g of x. So let me just take a screenshot and then put this right here. So which one, they gave f of x as ln of x plus 3, and they gave g of x as x to the fourth plus 2x cubed. So um, which one is on top and which one is below, right? So what's giving this right here is like, okay, you see that this thing is going up, this is going up. This looks like a polynomial right there. So honestly, you don't even know what you need to know what function it is. It's just like, okay, this bottom one looks like a polynomial, so g of x is a polynomial, so we have this right there. And then this looks like, um, pretty sure this is the natural log. Yeah, this has to be the natural log. Yeah, because think about it, right? If you put -2 into here, you have -2 comma 0 right there. So -2 plus 3 is 1, and the natural log of 1 is 0. So then, yeah, we have f of x up here. So then now in order to find the area of the region, you just do the bottom minus the top, right? So, and we're going from -2 to, is this 1? I don't think so, this is 1. We need to find the um, intersection points between f of x and g of x. So let f of x equal natural log of x plus 3, and then g of x equal x to the fourth plus 2x third. There we go. And I'm going to get rid of this. Okay, this is fun. Okay, yeah, we see this function up there. Anyways, on the calculator, you can figure out the intersection point. Well, it starts at -2, but it ends at 0.782. So we go to 2 to 0.782. Yeah, 0.782. We just need the x because we're just traversing through the x. We're taking dx integrals right there. So like we're taking little cross sections, vertical cross sections of dx thickness, and then we're going to add them to get an integral. Now we need the f of x, which is the top function, minus the bottom function. So it's f of x minus g of x dx. And you're given a calculator here, so you're expected to solve this. I don't want to rewrite this, but let's just put this in our calculator. Oh, this is -2, by the way. Integral of -2 to 0, 0.782 of f of x minus g of x. I should put this in brackets right here. So we're subtracting areas, top minus bottom, and then d of x. One element list. Oh, it's because it doesn't like these brackets, so I just have to be more specific. There we go. So we got 3.604, and that is the answer to 2A. But remember, this is just a guess. If you think I did it wrong, let me know in the comments down below. Let's go to 2B. Okay, for 2 is less than x, which is less than b. Let h be the vertical distance between f and g. Is h increasing or decreasing at 0. This is a very interesting b. What? B is just greater than 0. Okay. Um, Okay. Oh, okay. So this is like an optimization problem. So they're basically saying you got to be very careful. You got to be careful with words here. So here they're saying h of x is the vertical distance, right? Vertical distance, right? And then now if you want to say if h of x is increasing, right? If h of x is increasing, then the slope must be positive, right? And the slope in this case in calculus is h prime. That means h prime of x is greater than 0. And if h of x is decreasing, I'm just going to say decreasing, then h prime of x is less than 0. Now, they've given us h of x as this vertical distance, but what does this vertical distance actually represent, right? Over here, if you were to just look at it carefully, let's bring the graph back. This vertical distance is just f of x minus g of x, right? If you really think of it, it's just f of x minus g of x. And then you just get this vertical distance right here. So h of x, uh, h of x is just the top minus the bottom. So it's just f of x minus g of x. And then now, in order to see if it's increasing or decreasing, we need to see whether h prime is positive or negative. So now it's h of x equals f of x minus g of x. So then now you can just take a, well, I was about to say product rule. It's just the derivative of each of these. It's just f of x, f prime of x minus g prime of x. And then now, so then now, if you want to find the slope at negative 0.5, right? So it's h prime of negative 0.5 is equal to f prime of negative 0.5 minus g prime of negative 0.5. Uh, you could take the derivative of f of x. So f of x, that's basically just 1 over x plus 3. Yeah, that's just 1 over x plus 3. But then here you just have negative 0.5. And then for minus g, what is it? The derivative of that is just 3. Okay, I'm just going to write f prime is just 1 over x plus 3. And then g prime, just looking over here, you have x to the 4th plus 2x cubed. Now you take the derivative, that's 4x cubed plus, what is this? 6x squared? Yeah, 4x cubed plus 6x squared. Um, okay, so then now I'm just going to put this 4x cubed. Gonna give myself some more space. 4. See, this is like my downfall. I'm just completely messy. Uh, but here we have. So you could do that calculation. You can honestly just leave it as like this. Uh, but because I have this fancy calculator over here, I'm just gonna say we just need to find f prime, right? F prime of negative 0.5 minus g prime of 0.5. And that is negative 1.6. So the vertical distance, h of x, is decreasing because uh, um, because h prime of x is less than 0. Awesome. It was very similar to the previous question, actually. But all right. To move on to C. Again, these are all just guesses. If I'm doing something wrong, you can flame me. I have no regrets. All right. C. The region enclosed by the graphs f and g is the base of a solid. Cross sections of the solid taken perpendicular to the x-axis are squares. Find the volume of the solid. Okay. Cross sections. Okay. So I'm just gonna take a screenshot of this again. Oh no. I'm gonna bring this here, right? So these cross sections, what they're saying is just basically this top function, and how you understand the top is like top minus axis, subtract the bottom minus axis, but then the bottom is negative, right? So then you just add when you have negatives. Um, what happens is it just becomes positive, and then you get this big thing over here. So you need to understand that like subtracting the top minus the bottom gives you this length right over here from the top function to the bottom function. That's the one of the biggest concepts you need to understand here. But anyways, you're taking this function, right? And okay, come on. So you have this function right here, but if you extend this by 3D, right? I'm just going to extend this part by 3D, right? If we have squares, right, we can just take that side and then square it, and then at each interval, at each tiny, tiny interval, and then take all those squares together and smush them together, and then you can create a volume, right? So here, the cross section side length, right, is just going to be f of x minus g of x, right? That's the top minus the bottom. And then the squares, right? The side length squared. So square is just, I'm just going to say this is s, right? This is going to be s squared. And then what's our side? Our side length is f of x minus g of x. So then now we just square that. And then now we're going to add all those squares together by taking the integral. So taking from dx from the left-hand side to the right-hand side. And we got that b value from earlier, right? So we got -2 to this point right over here. We found out from our calculator, which is 0.782. And then now what we're going to take all these squares, that's f of x minus g of x whole squared, that just represents the squares that we're adding up. So we have all these squares, and then we have dx, which is a tiny interval, so we're adding multiple squares together, and this should be our volume. So I'm just going to take this, copy it, and then over here, I'm just going to put a square. Perfect. This should be 5.340. Again, if I did this wrong, flame me in the comments. Let's go on to D. A vertical line in the xy plane travels from left to right along the base of the solid described in part C. The vertical line is moving at a constant rate of 7 units per second. Find the rate of change of the area of the cross section about the vertical line with respect to time when the vertical position is at 0. X equals 0, -0.5. Okay, vertical line. Interesting. Let's see. So we have a vertical line. Goes to here, 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 here. Find the rate of change of area. Rate of change area. 7 units per second. That 7 units per. That is a very interesting question that I've never seen before, like ever. So let's try to problem solve. So if there's 7 units, right? That means it goes through 7 units. It goes from -2 to 5. Let's say, yeah, it starts. So it goes through 7 units a second. The vertical line x equals. So rate of change in area. So just area over time. Oh, area over time. So you just have to dA dt. Yeah, dA dt. So you have to take the derivative of this with respect to time? Huh. So it's a change in area over time. So the area is referred to as the area at the instant. I wish I can just come back to this, but let's just see. Area is just referred to as just like, okay, A to B. I'm just gonna have like constant placeholder right there. A to B of f of x dx. Area over time. I Find the rate of change of the area. See, this is like a good view of like how to actually problem solve, right? Because I am struck. Rate of change of the area. See, like I can calculate like a constant change. So for example, let's just say A over T, right? It's change in area over time. So in 1 second, I can go from what is it? From -1 to 0. That takes 1/7 of a second, right? Or x equals, it doesn't, okay. Sweeps. So it just sweeps. Do I need to do some like, okay, so 7 units per second. 7 units per second, that's a rate. But that's not the that's 7 units. So it's 1 unit every 1/7 of a second. Let's just keep that in mind. Okay, yeah, so let's just calculate the area from 0 to -1 to 0, right? Just from -1. -1 to 0 of a of t dt. They travel that in 1/7 of the time. Or, oh, a of x. Area is just nothing but f of x minus g of x. I'm just gonna say that. And then 1/7 of a second. So that's a change in area rate. Rate of change. Okay, let's just say we had a of x is equal to the integral from a to b of f of x minus g of x, right? This is the area. The rate of change. What I've just been like. Because I know, okay, so like if you take the area, I want to find the change in area, the change over time. That's just a dt. It's a dA over dt thing. Okay, I'm gonna give myself like 2 more minutes on this problem. And if I don't, then I am just, I'll just come back to it later, I guess. Is it like, okay, so like I know in like in 1 second, right? You can travel from -1/7 to 0. But like in a fraction of a second, like the rate of change. What is with respect to time. So like, okay, dx dt. Yeah, dx dt is 7 units a second. This is, oh, is this some chain rule stuff? No, no. Okay, uh, dude, dang. Oh my God. I think this is chain rule. Oh my, you kidding me? You're kidding. Okay, fine. Um, all right. So this dA over dt. Okay, so dx over dt, right? The change in the x over time, right? That's a constant. So dx, the smallest change in x over the smallest change in time, that's just 7 units a second, right? And then dA over dx, right? That's just the derivative of a with respect to x. So how are we going to find the derivative? So area is just this. Yeah. Okay. Then now how are we going to find? So is it? I think okay. So dA is equal to f of x minus g of x dx. Okay, if you think about it, right? So I'm working this backwards. Okay, I got this. I got this. Oh my God, I'm so happy. Um, but like say a of x is equal to, so this a refers to area, right? We have f of x minus g of x. It's the integral of f of x minus g of x, the top minus the bottom function, from like a to b of what is it, d of x, right? Okay, so then now what is it? Now in order to get a of x, right? This is basically the integral of dA of dx basically, or yeah, or like no, just the integral of dA, right? And if you take the integral of dA, that's just a with respect to a, right? So then the integral of dA is equal to the integral of f of x minus g of x dx. And then now both have integrals, so you can remove the integrals from both sides. So then d of a is equal to f of x minus g of x times dx. And then you can divide both sides by dx. So it's like the derivative basically. Oh yeah, you can also think about like the derivative of a of x, right? The derivative of an integral, right? Is just this function right here. So like you have like a, or like let's say random b. You take the integral, you make it bigger, right? Some big thing, and then you take the derivative back again. It's just the same b, right? So then now you just have, so you take the integral of this f of x minus g of x, and then take the derivative back again. You're just gonna have f of x minus g of x. All right. So now by chain rule, right? The change in area with respect to time is equal to just think about how units cancel each other out. dx dt times dA dx. So then dA dx is basically uh, f of, what is it? I think, yeah, it's negative 0.5 minus g of negative 0.5. And then they gave us the dx dt, or like the change in x over the change in time pretty much is constant, is 7 units a second. So then now we have this in basically now, yeah, this gives us something in units, and then you have units, and then you have units squared, right? Okay, so then now this is the big reveal. See, this took me way more than 30 minutes. I don't know, like this is actually a pretty wonky um, realization here. So what is f of negative 0.5? After all this time, I just realized it was chain rule. Oh my God. I'm so happy. I don't know why. I should have reviewed these earlier, honestly. But I feel like it's important for you guys to see this enjoyment. Um, 0.5. Can't type. 0.5. There we go. 7.727 units squared per second. See, this is in units. This gives you an answer in units, right? And this gives you an answer in units. Uh, so yeah, I'm pretty sure that is the answer. Hopefully that's the answer. If that's not the answer, I'll be pretty mad. Again, if you know the actual right answer, like let me know. But okay, let's move on to question 3. Dang. Okay, no calculators allowed for these. And fortunately, these are a lot easier. So, question 3. Okay, let's zoom in actually a bit. 3. So let f be a differentiable function with f of 4 equal 3 on the interval 0 is less than x is less than 7. The graph of f prime, the derivative of f, consists of a semicircle and 2 line segments as shown in the figure above. Find f of 0 and find f of 5. All right. So whenever they give you like f prime or something, and they feel like, okay, they give you like some, this is like an initial condition, condition. Um, and then there's like, okay, find f of 0, right? Then what they're trying to do is like they're saying, okay, whenever you take an integral, like especially like f prime, right, from a to b, this is the first fundamental theorem of calculus. So this is just basically you take the integral, right, which is f of x, and then you just take the top minus the bottom. So it's f of b minus f of a, right? So now whenever you have to find one of these and they give you another one, you can take advantage of both of these numbers right here. So um, the integral of the f prime of 0 to 4 is equal to f of 4 minus f of 0, right? And yeah, think about it. Just take the integral of f prime, then you're going to get f of 4 minus f of 0, right? From those specific spots. So then, now what you can do is integrals are nothing just but areas, right? So then, now we just find the area from 0 to 4, right? So from 0 to 4, we have this semicircle right over here. And the semicircle has a radius of 2, right? So the circle, the entire circle, if you do the area, it's pi 2 squared, but that's a full circle, so you have to divide by 2. So that's the area. So that's just this part right here. So that is equal to f of 4 minus f of 0. Well, f of 4 they've given us is 3. So then minus f of 0 is right here. So then now you can just solve for f of 0. So some algebra, which is 3 plus pi 2 squared over 2. I just left it as this. I don't want to. I got this on the BC exam, and I just left it as this. All right. B. Find the x. Oh, sorry, I forgot f of 5. Similar idea. I don't want to explain again. It's just like, okay, the integral from 4 to 5, right, of f prime is going to give you f of 5 minus f of 4. Again, fundamental theorem of calculus. So the area from 4 to 5 is just um, area from 4 to 5. This is half times 2, half times 1 times 1. That's just a triangle right there. Half times 1 times 1 uh, is equal to f prime, sorry, f of 5 minus f of 4. F of 4 is 3. So then f of 5, like now we do addition, is just 3 plus a half. Or you simplify saying 7 halves, whatever. There you go. Now let's go to B. Find the x-coordinates of all points of inflection of the graph of f for 0 is less than x is less than 7. Justify your answer. All right. So here, what we're going to do is points of inflection. Okay, so f points of. So let's think about this realistically in terms of graph, right? So if you had f, right, point of inflection would look something like this. And more specifically, it's right there. It's like when something goes from concave up to concave down, or something goes from that's that's basically saying the same thing. Something goes from concave down to concave up, or something. At that point, that's called a point of inflection. That's when it changes concavity, right? So then now, if you were to draw f f prime, right? If you were to draw f prime at that particular spot right there, you see that the slope is increasing. So increasing, so when it's concave, the slope is increasing at an increasing rate. So then now the slope will be up like this, right? So, but then at this point of inflection point, you see that the slope is decreasing, which means like, let's say this is positive, right? So the slope is still positive, but it's less positive, right? So it's less positive. So these numbers over here, the y-axis represent the slope, right? So you're going to have a smaller slope, but it's still going to be a positive slope. So let's cause this to come down right here on the f prime. But over here, we see at this point of inflection, that's when f prime has reached a maximum. And similarly, if you go from concave down to concave up or something, you'll realize that So here, the slope is getting small, it's getting steeper and steeper. This negative slope, so if you're to go right here, this negative slope is getting steeper and steeper. And then over here, you still have a negative slope, but it's getting closer towards zero, right? So then now you have this f prime graph over here, and you see f prime has a minimum right over there. So then when f prime has a minimum or a maximum, then f has a point of inflection. So here we have the graph of f prime, and now we need to do is to find the minimums and the maximums, and those are our point of inflection. So we say x is equal to 2 and x is equal to 6 because this is a rel min and a rel max. Rel is just relative of f prime, and that shows you point of inflection of f of x. Awesome. Let's move on to C. Okay, let x be the function defined g of x is equal to f of x minus x. On what intervals, if any, is g decreasing? So it's the same idea. Okay, so g is decreasing, then g is decreasing. Ooh, g is decreasing. What's the slope? Ooh, the slope is negative, so g prime is less than 0. So then now, over here, g of x, g prime of x, we just want to see g prime of x is equal to f prime of x, just the derivative of f, and then we subtract from 1, right? So then, on what intervals is g of x equal to x? One is this g prime less than 0. And this is kind of a weird one, actually, if you really think about it. But if you're pretty fancy with graphs, I think it'd become a lot easier. So whenever you subtract a graph by 1, so let's say you had like y is equal to 2, right? And you subtract by 1. Oh no, I bumped down 1, right? You bump everything down by 1. So here, this f g prime is equal to basically f prime, which is what you have right over here. You subtract by 1. You just bump everything down by 1. So here's at -2, now it goes to -3, right? So then you can just draw, yeah, you can kind of draw what happens. Um, you don't need to draw it like perfectly, but right here, now we see, okay, when this is g of x, right? G prime, sorry, g prime. And g prime is just f prime, which is the one above, subtract by 1. And now we have g of x. So now, sorry, we have g prime. So then g prime is less than 0 from 0. I mean, you start from 0, and it goes from 0 all the way to 5, right? So 0 is less than x, which is less than 5. That's when it is decreasing, when g is decreasing, because g prime is less than 0. Awesome. Let's move on to D. Huh. Okay. D. Okay, for your function defined in part C, find the absolute minimum value on the interval, which 0 is less than x, which is less than 7. Justify your answer. Okay, so finding the absolute minimum of the value. So, honestly, I hate these questions a lot, but so whenever you have a minimum, right, of g of x, let's say the minimum of g of x, then the slope, right, which is basically g prime is equal to 0. But another thing about minimum is a slope changes from a negative to a positive. So g prime goes from neg to pos, right? So what we have here is at x equals -2, right? So at x equals -2, we have, that's our minimum, or that's when, okay, no, that's bad terminology, never mind. We need to find when this is equal to 0. So 0 is equal to f prime of x equal to 1. So prime of x is equal to 1. So then now we need to find when f prime of x is equal to 1. Yes. Now we need to find when f prime of x. Wait, is it? Yeah. Okay. Actually, yeah, that's right. Okay. Prime of x is equal to 1. Oh, over here we see that from 4 to 6, I think, slope is 1. Oh, we just need to see a value when f of prime. Sorry, yeah, okay, I get this now. So we need to see, okay, when is f prime of x equal to 1? Well, over here we see f prime 5. So this is f prime 5 is equal to 1. But then now we need to see if, oh yeah, and if we look at our graph from here, this is g of x, right? So then now we need, sorry, g prime of x. And whenever we want to see a minimum, we want to see g prime is 0, right? And over here, x equals 5 is 0. So yeah, so at x equals 5, the g prime of x is 0. But we also need to check minimums and maximums, right? So the slope needs to change from negative to positive. And over here, if you look at this graph, the slope changes from negative to positive. It goes from a negative, so I'm talking about slopes in terms of derivatives, so f prime, right, goes from negative to positive, which means it's an absolute minimum of g. So then therefore, x equals 5, that's where the minimum occurs, absolute minimum occurs because g prime is equal to 0, and g prime changes from neg to positive. All right, we're done with that. We just hit the halfway mark. Yeah, but let's just continue as much as I possibly can, and I'll just continue it later. But okay, ice sculpture. Everyone should. So, okay, ice sculpture melts in a way such that it can be modeled as a cone that maintains a conical shape as it decreases in size. The radius of the base is given by twice differentiable function r, where r of t is measured in centimeters and t is measured in days. The table above gives selected values of r prime of t, the rate of change of the radius over the time interval 0, which is less than or equal to t, which is less than or equal to 12. Approximate r double prime 8.5 using the average rate of change of r prime over the interval 7, which is less than t, which is less than 10. Show the computations that lead to your answer and indicate units of measure. All right. Let's see. R double prime of t. R double prime of t. Okay. So R double prime. Okay. We need to first do. Okay. What is R double prime first of all? R double prime is r r prime of t, right? It's the derivative of r prime of t. That's what r double prime of t means, right? So, okay, average rate of change. That's literally slope. It's like, okay, on average, how far is this changing, right? So from one point to another point. So it's like, okay, on average, it's changing at this rate, at this slope. So what we can do is we can just take the slope of r prime of t, and that will give us our approximate of r double prime of t. So then I can say r double prime of 8.5. And then for the slope, you want to get as close as you possibly can. So 8.5, that's like right in between 7 and 10. So that's why I'm going to be as close as possible. So I'm just going to say r prime of 10 minus r prime of 7 over 10 minus 7. The change in y, which is the r prime of t, think of it, r prime of t over t, that should give you approximately the slope of r prime of t, which is r double prime, right? So then now we have r prime of 10, which is negative 3.8, r prime of 7, which is negative 4.4, and then we have 10 minus 7. And then I just left my answer like this. I'm not going to calculate that. All right. Like you've probably realized by now, my weakness is actual math. But um, anyways, let's move on. Is there a time t uh, for 0, which is less than or equal to t, which is less than or equal to 3, for which r prime of t is equal to negative 6? And honestly, you can't really answer this without knowing one of the theorems of calculus. There's, okay, besides first and second fundamental theorem of calculus, there's IVT, MVT, and what's that? Extreme value theorem, EVT. So here, um, which one, to remember which one is which, extreme refers to extrema, or like think about maxes or mins, right? Um, so it's like this theorem says like, okay, if you this interval is continuous, there's going to be an absolute maximum and an absolute minimum. It's an absolutely garbage theorem, but yeah, that exists. And then now mean and intermediate value theorem, they exist a lot more. So mean value theorem is like if most people remember as the AROC equals IROC thing, which is the average rate of change is equal to instantaneous rate of change. But more specifically, if you're to think about it, if you're to have some sort of like curve, so let's say so from A to B, right? Um, and it's continuous and differentiable on the interval from A to B, like say you had A and B. If you took the derivative of that, then there's going to be another point C. Sorry, this is not the derivative. If you just take the tangent, no, secant line. It's called secant line. If you take the slope between A and B, then on that interval, there's a point C where the derivative is equal to the rate of change. So this would be like the f prime of C, and this is equal to the f of B minus the f of A over B minus A. This is just slope, and then this is just the derivative. So that's what mean value theorem is. But here, what we're trying to use is, okay, um, is there a value from 0 to 3 for which r prime of t is negative 6? And intermediate, think of intermediate, just think of it as like in between theorem. So here it's like, okay, if you have an interval, let's say, yeah, let's just do this problem right here. If you have this interval from 0 to t to 3, right? That means from this interval, you're going to have some sort of f of t, right? Where, or in this case, I'm just going to say r prime of t, where you go from, I mean, yeah, sure, you can just say r prime of 0 t, which is less than or equal to r prime of t, which is less than or equal to r prime negative 3. Or you can switch them around, whichever is bigger. But you're going to have a range that goes from, in this case, negative 6.1 to 5.0, right? Think about it. If you had this graph over here, yeah, if you had this graph over here, let's say this is x equals 2, and then let's say x equals 5, and let's say this is 4, and then let's say you had 7, right? If this is continuous, then you're going to have all the values from 4 to 7. So you're going to have 5 in here, you're going to have 6 in here, you're going to have 5.5 in there. Basically, this theorem is saying the exact same thing for this scenario, right? You have negative 6.1, you have negative 5.0 in that interval. So you should have negative 6 in there as well if you're going to be in between. So that's why we're going to use the intermediate value theorem to show that negative 6.0 is in between negative 6.1, negative 5.0 from time 0 to 3. So therefore, this is true. There is going to be a time where r prime of t is equal to negative 6 because of the intermediate value theorem. All right, C, 4C. Use a right Riemann sum with 4 subintervals indicated in the table to approximate the value of 0 to 12 r prime of t dt. Okay, so this Riemann sum stuff, fun. First, what I like to do for Riemann sums is I like to draw a table. Sorry, not a table. I'm blanking. I like to draw a graph or some sort, right? So usually here, this is negative, right? So then I just like to make, okay, so this is like 0, this is like 3. Dude, just drew the same thing all over again. That's fun. So say you have 0, 3, 7, 10, 12, something like that, right? And then you had 0 is like negative 6.1, right? I'm just going to draw like negative 5.0, negative 4.4. So you're going to have something like this, right? And now if you want to do right Riemann sum, then what you need to take the right point, and then you need to take the rectangle based on there, right? So then I'm just going to draw a bunch of rectangles there, and boom, now I just take the area of right over here. So this length is 2, this length from 3 to 7 is 4, this length from 7 to 10 is 3, and then this length from 10 to 12 is 2, right? And then this is minus 5, right? Because they're taking the right length. This length is minus 4.4. This length is 10, and then this length, oh no, not 10. I'm goofing up. This length is negative 3.8, and then this length is negative 3.5. So now we just add all those up together, so it's 3 times 5, and then so we get this over here, plus, what is it, 4, that's the width of this rectangle, times negative 4.4, which gives you this rectangle. You have 3 times 3.8, negative 3.8, which gives you this rectangle. Then you have 2 times 3.5, which gives you the last rectangle. And that is how you approximate Riemann sum. So there we go. I think we're done there. Okay, I think this is everyone's favorite question. Because this is now we're dealing with the actual cone and actual related rates. And I knew there was going to be a related rates problem on the FRQ, but let's do it right here. The height of the cone decreases at a rate of 2 centimeters per day. Oh, I screwed this up on the exam. Fun. Uh, I don't know what I. Oh yeah. Okay. Yeah. Okay, I screwed this up on the exam. I just realized that right now. I like literally my mind just kind of like blew up on the exam. Um, I thought the radius of the cone was decreasing at a rate 2 meters per day, and I just assumed that. I do not know why. But okay, I'll do it right now. dH over dt, right? Let's just pause. Okay, actually, let's read the entire question. The height of the cone decreases at a rate of 2 centimeters per day. At time t equals 3, the radius is 100 centimeters and the height is 50 centimeters. Find the rate of change of the volume of the cone with respect to time in cubic centimeters per day at time t is equal to 3 days. Okay, the volume of V, a cone with radius r and height h, is the following formula. So my first step in any related rate problem is to take the formula, right, and have the formula with you. Fortunately, they gave us a formula of a cone. If we had to remember the formula of a cone, I don't think most people would have gotten this question right. But anyways, right, now we want to find rates, right? And rates are in terms of time. So the fun thing about equations is we can take the derivative with respect to time. So then the left-hand side is dv dt, and the right hand side, we have this 1/3 pi, which is a constant. And then now we have this r squared h business, right? And r squared h, that is a product. So then we can use the product rule. So we take u prime, I'm saying u prime v plus v prime u. So u prime is it's r squared, which is 2r. But remember, we're taking the derivative with respect to t. So because of chain rule, it's dr dt times h plus v prime, which is dh dt uh, times uh, what is it times? Okay, why am I blanking? It's just r squared, right? U is just r squared. All right. So then now, we're trying to find this, right? So basically, we just by differentiating the formula, you can just figure out, okay, find the rate of change of volume with respect to time, which is dv dt, the change in v over the change in t, right? But then now you have 2r dr dt. Now you have all this other business right here, right? So now in cubic centimeters per day. So then we can just keep these 100 in centimeters. So then now just plug in information, right? So 2r, uh, so then now r is what? R is the radius, right? And the radius is 50 at t equals 3 days, right? The height is 50. They say at t equals 3, the height is 50. Um, times dr over dt. Now, okay, what is dr over dt? Hmm. That is a question a lot of people question themselves like, okay, how fast is the radius changing? But there's a very sleek observation that you need to be made over here. Whenever you have a cone, right? And whenever something's like decreasing or something, like the ratio between the radius and the height remains the same because you have that if you look at a cross section, um, what is it? If you look at smaller and smaller in triangles, the ratio, because how similar triangles work, the ratio between the height and the radius remains the same. So over here, they've given us that the radius is 100 centimeters and the height is 50 centimeters, right? So the height times 2 is equal to r, right? Or 2h is equal to r. And let's say if we split so let's just make this right here, right? We had 50 centimeters and we had 100 centimeters, right? So if we split this in half, then if the radius were 25 centimeter, then the height would be 2 times the radius, which is 50. So then you have 2h is equal to r, right? So then now you can, again, because we have equations and we're in calculus, you can take the derivative with respect to time. So then you have 2h uh, dh dt because of chain rule is equal to dr dt. And whoa, we got something. Now, what is dH dt? dH dt refers to the what is it? How fast the oh no, I screwed this up actually. What is this? It's just two. It's just two. So we have this two constant, and then we have two dh dt. It's equal to dr dt. So then dh dt is how fast the um, height is changing, and they said it decreases at a rate of 2 centimeters per day. So then this is -2 centimeters per day. But honestly, who cares about units, right? I mean, you should know what the units represent, but this is -2. So that means dr dt is -4, right? So then now we can just plug this in back into our equation right over here, which dr dt is -4 times h, which is 100, sorry, 50, plus dh dt is 50. No, sorry, dh dt is how fast it's decreasing. So that's -2 times r squared. So that's 50 squared. And that, my friends, is the rate of change of the volume with respect to time. I just took this formula, did some bunch of product rule, bunch of chain rule. You got to realize this relationship between dh and dh dt and dr dt. The radius. Oh no, okay, I did this right. I did this right. What is it? 2h, 2 times the height is radius. I probably did this diagram incorrectly. Um, the radius is 100 centimeters and the height is only 50. So this is actually a pretty wide cone right here. So you have 100 centimeters and then you have 50 centimeters. But yeah, the idea is like the ratio between the radius and the height always remains the same because of similar triangles. But anyways, what is it? The height, the radius changes 2 times as fast as the height. So if the height changes at -2, then the radius, because it's 2 times as big, will change at -4. Then we just plug in all that in, and boom, we have that right there. I probably did some math there. That's who I am, but I don't have the energy or mental capacity to go through it. I think as long as you get this, at least this formula, you would get most of the points. The answer is probably just 1 point. So it's the process that matters, not necessarily the answer. Oh, differential equation's fun. Consider the differential equation dy dx is equal to that. Yeah. Let y equals f of x be a particular solution to the differential equation with the initial condition f of 1 equals 2. Okay. Oh, so it's just a sketch. Whoa. I did not know that. Okay. Let's zoom that out. 1 comma 2. So of course you're gonna have 1 comma 2, which goes to right there. Uh Honestly, you just follow the line. Yeah, you just follow the line. So here you go like here, 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 right? This is fun. It's honestly, you just follow the line. And yeah, that looks like a sine, cosine, whatever, right? You know, the derivative of sine is cosine, right? So yeah, you just sketch this. You just sketch it. That's all. You just like, okay, the slope is 0, then okay, then it has 0, right? Or if the slope is like negative, it's like negative. You basically just sketch it. So that's easy point. That's probably just 1 point though. Anyways, write the equation tangent to the solution curve and uh, write an equation for the line tangent. Okay, so tangent lines, you need the following, right? You need slope, and then you need the point. You need the xy coordinates. So at 1 comma 2, right? So the x coordinate and the y coordinate, right? That's just going to be 1 and 2. And then the slope is just we find dy dx. And then we put this all into the slope point formula right here. So dy dx. I mean, you could understand how this works. It's a change in x over the change in y. This is the change in y, and this is the change in x. And then this is the slope, right? So the slope times the change in x. Right? Okay, let's just say this is approximate, right? Change in y over change in x, right? So then if you multiply both sides by the change in x, you get the slope point formula right here. So you have any y minus x over that x that corresponds to that y. So it's like assuming that you have a coordinate xy, x0 and y0 are your actual points. So let's actually just plug this in right here. For y minus 2 is equal to dy dx over x minus x naught. Sorry, not x naught. This is x minus 1 right there. And then now we need to find dy dx, right? And dy dx they've given us by this right here, half sine pi over 2 x plus this times square root of y plus 7. So here, what we're going to do, yeah, we just plug in 1 comma 2 into there, right? We're given 1 comma 2. So just sine of pi over 2, right? Plus, I mean, 2 plus 7 is 9. Of course, show more work than this. I'm just lazy. Sine of pi over 2 is 1. You know, your unit circle, it's amazing. Half times 1 times 3, that's just 3 halves. So then now you just plug in 3 halves into there, and we have this beautiful tangent line. Wonderful. Okay. It is known, okay, let's go on to 5c. It is known that f double prime of x is greater than 0 for negative 1, which is less than or equal to x, which is less than or equal to 1. Is the approximation found in part B an overestimate or an underestimate for f of 0? I forgot. I got to plug in 0.8 into there. So I'll just be like y is equal to 2 plus, and then just plug in 0.8. Don't even need to do the math. Fun. Okay. Then now f double prime is greater than 0. So the approximation an underestimate or an overestimate. Give a reason for your answer. Well, this requires some thinking, right? So let's just say you had a curve and its f double prime is greater than 0. If you know, that means the slope is increasing at an increasing rate, which means that it's going to be concave up, right? It's increasing at an increasing rate. That's what this f double prime means, right? So think about like acceleration, right? We see like the position curve, it just goes whee, right? So similarly, we're going to do something like that for just this is f when f double prime is greater than 0. Anyways, so at this particular point now we have a tangent line that goes through, right? And if it's f prime is greater than 0, right? Any point, as long as it's concave up, it's going to be greater than what we expected. So our thing is an underestimate. Because f double prime is greater than 0, so it's concave up. So all these other points that, oh, this is at x equals 1, right? So then if it was like x equals 1 is going to be exact, right? Because this tangent line matches with the curve. But like at 0.8, for example, or like 1.2, for example, all of it's just going to be above the curve. So our approximation is an underestimate because f double prime is greater than 0, so it's concave up. So it flares up, it's greater than the curve, and yeah. Separation of variables. Honestly, these BC questions, AB questions are not terrible. They're not terrible, but half sine of pi over 2 x. Okay. So then now separation of variables, at least they told you to separation of variables, but like that's the only technique that you really know. Basically separation of variables, you put all of the y's on one side, all of the x's on the other side, and you take the integral. So let's just do that right now. That's 1 over the square. Oh, never mind. I can see why this takes some time. Half sine, half pi over 2 x dx. Right, and then now we take the integral, right? So we have an integral of dy and an integral of dx. Here, what would I do here? Oh, this is like u sub in both ways, right? So let's just say, because I know that the integral of 1 over 2 to the x, I just know because I am a nerd. But oh yeah, you can have plus c, whatever. But like I know the derivative of this is equal to that because if you just do what is it called? Derivative, what's that called? Power rule, right? You just do half times, right? And you get something like that, and then that's just that. So you can reverse that in the other direction. And this looks kind of similar, right? So I probably want to use something like that for u substitution. So I'm going to say let u equal y plus 7, which means if I want something for dy, right? If I just take the derivative, so du with respect to dy, just take the derivative of both sides is equal to 1, and then derivative of constant is 0, right? So that means du, if you multiply both sides by dy, yeah, du is equal to dy. So then now we just have, I should say u is equal to y plus 7, right? So we have 1 over root u du, and I know I can multiply 1/2 inside the integral. So that's going to be 1 times 2. I'm just going to put this strategically here. And I multiply 2 outside the integral. So I can balance everything out. And then this equals, okay, this is fun. You could use, yeah, sure. You can say let u equal pi over 2x, and then du over dx, the derivative is, what is it, pi over 2. So then du is equal to pi over 2 times dx, right? So then now, what is it? You can multiply by pi on the inside, so half times pi is equal to pi over 2 dx, and then on the outside, in order to balance it, you can multiply by 2 over pi, because 2 over pi times, oh, sorry, no, my bad. Actually, I think an easier way to solve this is, you can solve for dx instead of du, right? So then you say dx is just du over pi over 2 is equal to dx. And then you can just plug this in right there because dx is right there. So then that's just basically 2 over pi du, right? Okay. I shouldn't be using u. I should probably be using some other letter here like v, dv, 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 x, right? It's the same idea though. So now what we're going to do, these equal to each other. So I'm going to have, we have this left-hand side already. 1, 2 du is equal to 1/2 sine u. It's going to be sine of u. And then we have this 2 pi thing, 2 over pi du. And how I figured that out was just by taking the derivative and then finding what dx was. There's two ways. Otherwise you could have just done whatever I did. I just multiply by pi on the inside and you divide by pi on the outside, and you get the same result regardless. But anyways, this is the integral of 1 over 2 over root u is root u. That equals what is it? Half times what is it? The derivative of is a negative sine. Sorry, the derivative of sine is negative cosine u. Oh yeah, and we had this root 2 over pi thing, so that's just 1 over pi, right? 1 over pi cosine u plus c. Oh yeah, these are v's, my bad. So then now I'm just going to replace everything. To u was y plus 7, and then v was, what is it? V was pi over 2x. There we go. And if you take the derivative of this, you can be like, okay, this is negative sine, so you have sine, the negative cosine, the derivative of negative cosine is sine. You have these pi over 2x, and then you multiply by pi over 2 to this, and then you get like 1 over pi times pi over 2 is just 1/2. So we did the derivative on the right side. So the integral works out fine. And of course you have the plus c. This is really nasty. Okay, but let's just divide everything by 2. So we have the square root of y plus 7 is equal to 1 over pi cosine pi over 2x plus c. Then you take if you multiply by 2, you have this 2 pi. And then when you multiply 2 times c, right, that's just, oh, we're not dividing. We have to divide by 2. Oopsies. So that'll just be 1 over 2 pi this, and then c divided by 2 is just c, just a constant, right? And then when you square it, right, here you do need to include c in there though, they're pretty nitpicky about that. So you have this right there. Then you can subtract 7. But I'll just do all of it in one step. So y is equal to 1 minus 2 cosine pi over 2x plus c squared minus 7. And then now initial condition, you want to figure out what c is, right? What we need to do is you would need to plug in 1 into here and plug in 2 into there. So 2 is equal to negative 1 over 2 pi cosine. I mean, if I put in 1 here, cosine of pi is 0. So this term just goes away, right? Cosine of pi over, yeah, because 1 you put in there, cosine of pi over 2 is 0. Then, yeah, all this term goes away. Then you have this c squared is equal to 7, right? So then c is equal to 3. So then, yeah, there we go. So then therefore y is equal to negative 1 over 2 pi cosine pi over 2x plus 3 squared minus 7. That was fun. No, it was not fun. Okay. All right, let's move on to question 6. I think I explained this way too much, but particle P. Okay, this does not seem too bad. So we'll do part 6, and then we'll go back to 1, where I think I screwed up a lot, actually. Okay, 6. Particle P moves along the x-axis such that t is equal to 0. X of position t is equal to 6 minus 4 e to negative t. I can't say anything today. Particle Q moves along the y-axis such that for time t is greater than 0, velocity is given velocity of Q. Oh, I remember a question like this last year. I don't know. And then at t is equal to 1, y Q of 1 is equal to, it's like last question. Okay, never mind. Find v of p of velocity of particle p at time t. Okay, so you just need to know that the change in, the change in position, the change in x over time, isn't that your speed or quote unquote velocity, right? So then now if you're to take an instantaneous change in distance or displacement divided by time, that's going to be your instantaneous velocity. So it's dx dt is equal to velocity. So now we take the derivative of our position of p, right? So then that's just going to be 6 minus 4e to the negative t. And that is going to be our velocity v. We're going to call this vp of t, right? So then now this is just 6 just goes away, and now you have negative 4. I mean, the derivative of e to the t, or e to anything, is just that by itself times the derivative of the power, which is negative 1. So that's going to be 4e to the negative t is equal to vp of t. And that is A. Awesome. Let's move on to B. Find A of q of t. Find all times t. Okay. So acceleration, again, acceleration is how fast something is speeding up or slowing down. So it's how fast the speed is changing. So speed is velocity. So the change in velocity over the change in time is the average acceleration. But now if we take the smallest change in velocity over the smallest change in time, we can see how the velocity is actually changing. So that is dv over dt is acceleration. Now, that's the derivative of velocity. The derivative of velocity of position of particle q, that is 1 over t squared. Or I'm going to write that as t to the power of negative 2 is equal to a. So then now if we do power rule, then we get negative 2t to the negative cube is equal to a. I think we should say a q of t. So right there. Awesome. So now we need to find all t. So then, like, okay, so let's say this is basically negative 2 of t of, what is it? Negative 2 of t Okay, so you need to find all times t greater than 0 when the speed of particle q is decreasing. Okay, so then now this is this increasing, decreasing stuff that we see all over again. So it's like if velocity is increasing, right? Let's say increasing, then what is it? V prime of t, the slope of velocity, aka the acceleration, is greater than 0, and we can say the vice versa, right? So then here, v prime of t, this is how to solve v prime of t, right? This number, this a, is always going to be uh, less than 0. Sorry, this is always going to be positive right over here. But we have this negative over here. Negative divided by positive is negative. So you're always going to have a negative acceleration. So you have, what is it, v of t is less than 0. So it's going to be decreasing. And what is it, v prime of t is less than 0, right? And then, but the thing is with speeds, right? We have to make sure the speed is always going to be greater than 0 here. Because if you have, this is just a weird thing. Um, if something is speeding up, then velocity and acceleration, or v prime of t, have the same sign. Uh, so yeah, it's like, let's say you have like 5 meters per second to the right, and you have an acceleration of 2 meters per second, like 2 meters per second per second. That means you're increasing your velocity to the right, which means you're going to get faster and faster as you go to the right. But let's say you have a speed of, a velocity of -5, but you're going to the left, or in this case, I don't know what you can see, but like you go to the left, and then you have an acceleration of -2 meters per second per second. So let's say you're going this way, and then you have an acceleration that's pushing you more to the left. You have a negative velocity and you have a negative acceleration, but you're speeding up. So it's only when like you have a negative velocity and a positive acceleration that's causing you to decrease speed at first, right? So it's pulling you, it's trying to pull you to the other side. That's what like forces are, right? But like let's say you go from -5 meters per second, and you have a positive acceleration like -2 meters per second squared, and like 1 second later you're at -3 meters per second. You're still going to the left, but you're decreasing your speed, right? So you're decreasing your speed, but you have opposite signs, and you can do the same thing in reverse. So if it's speeding up, then they have the same sign, but if they're um, slowing down, then what we say is v of t and a of t have opposite signs. So here we'd be like for t, what is it? If you look at v of t is just 1 over t squared. Um, and as t approaches infinity, right? Or for t greater than 0, this is going to be positive. T squared is always going to be positive, right? And 1 is always positive. So you're going to have a positive velocity, but you're going to have a negative acceleration because you have a positive velocity and a negative acceleration. Negative acceleration seen up here, where negative or positive. Um, Therefore, you're going to have opposite signs, and therefore it's slowing down. So slowing down is the correct answer, and saying velocity is positive and acceleration is negative. All right, C. Um, Find yq of t, the position of particle q at time t. Uh, mm, oh, so that's just, okay, so then now this is like integration, right? So the change in velocity times time, right? Let's say again at the very beginning of this lesson, that 60 miles an hour multiplied by some sort of time, you're going to get the actual distance that you travel. So here the integral of velocity is position, because the change in position over multiplied by some sort of time, which is our dt, right? So it's like our v, I think that's vqt multiplied. This, remember, these two are multiplied to each other, and then these are summed together in an integral, right? So now we go from, okay, we know from, uh, okay, if you were to just take the integral of this, right? Yeah, let's just take the integral of this. That's yqt. I hate v's and y's. They look exactly the same for me. But okay, that's just the integral of 1 t squared. This is just negative t to -2 dt. So then now we just do the reverse power rule where we add 1 to the power, and then we divide by that power plus c, right? And then, so we have -1 over t plus c is equal to y q of t. And then now we can, in order to find this initial condition right here, we just plug in 1 into there. So 1 wherever we see t. So it's -1 plus c is equal to yq of 1. Yq of 1, according to the test, is 2. Then c is equal to 2 minus -1, which is equal to 3. So then therefore yq of t is equal to -1 of t plus 3. There we go. All right. And then one more question, and then I skipped one at the very beginning. I'll come back to it. 6D. As t approaches infinity, which particle will eventually be farther from the origin? I'm assuming origin is 0, 0, or farther position. Well, okay, so this is 6. X is equal to 6 minus 4e. Yeah, e to the negative t is just basically saying 1 over e to the t, right? And as t approaches infinity for this, right, this becomes infinitely large. This denominator becomes infinitely large. So this goes to way. So this is approaching 6. And then from above, we got y cube of t, right? That's equal to -1 plus t over 3, right? And as t goes to infinity over here, the denominator gets infinitely large. So when you divide that by that, this approaches 0, right? You have such a large denominator that it's pretty much like 1 over a billion, 1 over a trillion. Like it's so much smaller than that. You can just say it's 0. So it's as t approaches infinity, it's going to 3. So this is at x equals 6, and this is at y is equal to 3 as x approaches infinity. So then therefore, I think the answer to this one is particle Q will be closer to the origin, because t approaches infinity for both of those, x approaches 6, and y approaches 3. Yeah, and then they're traveling along their respective axes. So if it's x equals 6, the coordinate will be 6, 0, and for y this will be 0, 3, and this is 3 units away, this is 6 units away, and therefore particle Q will be closer. All right, let's do that last question, 1D, because honestly, I kind of left it blank on the test. But we'll see. A line forms when A of x minus 400 dx A to t. The line forms whenever A of t is greater than 400. A is first to the nearest number. Find the greatest number of vehicles. All right. So here, I'm just going to bring this to the right-hand side. Then take this right. So we have this A of t right here. So then now we need to see, if we said when A of t, or it's like, let's just say, let's get rid of this f of x and g of x. Let's just say this is, let's just say y is equal to 400. And yeah, where is 400? Oh. Is it even seen? Can you even see this? Oh, there we go. So let A be the first time. So that's 1.469, right? So what we're now trying to do is we're trying to find what is this time? 3.598. Okay, yeah, what we're trying to do, I think we're just trying to find the maximum area, right? Under this. We're trying to maximize N of t, number of vehicles, find the greatest number of vehicles. So we're just trying to maximize this. So we maximize this, we need the most positive area. So we go from 1.469 to 3.598. And then, yeah, once you go to 4, right? Like once now you're getting negative area. So like we're just trying to maximize this. So we want the greatest area under this. So honestly, you can just even subtract this by, so it's a of t minus 400, right? So this is a of t, you can minus 400. And then uh, a of t, okay, honestly, this is probably not the best idea, but, oh, did I say 4,000 on accident? No, I said 400. Okay, I think it's honestly better to just look at this graph this way. Uh, but you have to go from -1 to this, so that's how you get the maximum positive area from there. So that was the integral from 1.469 to 3.598, 3.598 of a of t minus 400 dt. That does not seem right. Oh, that's just the air. Yeah, no, did it? Oh, okay. I think that is that right actually. 71 point. So that's when the line forms whenever a of t is greater than 400. So then this one it's 400, and then yeah. So that's when line forms at 1.469, and then we just take the maximum area of a of x from that point onward, 3.598, and yeah, that's it. That's pretty much it. Because other than that, now you're just gonna start decreasing area there. But that's pretty much it. Um, so yeah, I guess that's, I'm pretty sure this would be the answer. 71.25, that would be the greatest answer for there. But other than that, I think we've hit the 1 hour 30 mark. So that's pretty much it. Thank you guys for watching this AP Calculus AB um, exam walkthrough. If you have any questions, please let me know in the comments down below. If I messed up, please let me know in the comments. Well, other than that, if you have any other requests or any other suggestions, please let me know. Well, other than that, that's it from me today. Okay, thank you. I'll see you later.